The most profound question. Throughout human history, we have gazed at the stars and wondered, are we alone? This question has captivated philosophers, scientists, and dreamers for millennia. Today, as our telescopes peer deeper into space and our understanding of biology grows more sophisticated, we stand at the threshold of potentially answering this ancient mystery. The search for extraterrestrial life has evolved from speculation into serious scientific inquiry, and the evidence we've gathered suggests that the universe may be teeming with life in forms both familiar and utterly alien to our understanding. The question of alien existence isn't merely academic curiosity. It touches on fundamental aspects of human identity, our place in the cosmos, and our future as a species. If we are alone, we bear a unique responsibility as the universe's only conscious observers. If we are not alone, then first contact could transform human civilization in ways we can scarcely imagine. Every telescope pointed at the sky, every rover crawling across Mars, every radio antenna listening for signals from the stars represents humanity's collective attempt to answer this most profound of questions. The mathematical argument, Drake's legacy. In 1961, astronomer Frank Drake formulated an equation that would become central to the search for extraterrestrial intelligence. The Drake equation attempts to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. While we cannot solve it definitively, the equation forces us to consider crucial factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually develops, the fraction where intelligent life evolves, the fraction that develops detectable technology, and how long such civilizations last. Even with conservative estimates, the numbers are staggering. Our galaxy contains roughly 200 to 400 billion stars. Recent discoveries by the Kepler Space Telescope have revealed that most stars have planets, and a significant fraction of these exist in the habitable zone where liquid water could exist. If even a tiny percentage of these worlds develop life, and an even smaller fraction develop intelligent life, we could still be talking about thousands or even millions of civilizations in our galaxy alone. And remember, the Milky Way is just one of an estimated 2 trillion galaxies in the observable universe. But there's a darker interpretation. Enrico Fermi famously asked, "Where is everybody?" This Fermi paradox highlights a troubling contradiction. If intelligent life is common, why haven't we detected any signs of it? The silence could mean that life is extraordinarily rare, that intelligent civilizations inevitably destroy themselves, or that we're looking in the wrong way or at the wrong time. Each possibility carries profound implications for humanity's future. Some scientists have proposed solutions to the Fermi Paradox that don't rely on rarity or doom. Perhaps advanced civilizations deliberately avoid contact with primitive species like us, a concept known as the zoo hypothesis. Maybe the vast distances and timescales involved make contact statistically unlikely, even in a universe full of life. Or perhaps intelligence typically evolves in ways that don't involve radio communication or space exploration. Maybe consciousness usually develops in ocean depths or in forms we wouldn't recognize as intelligent. The building blocks. Life's universal chemistry. One of the strongest arguments for extraterrestrial life comes from chemistry itself. The elements that make up living organisms on Earth, carbon, hydrogen, oxygen, Nitrogen, phosphorus, and sulfur are among the most abundant elements in the universe. Carbon's ability to form complex molecules makes it the ideal backbone for life's chemistry. These fundamental building blocks exist everywhere we look in space. We've discovered organic molecules, the carbon-based compounds, essential for life, as we know it in interstellar clouds, in comets, and on asteroids. The Murchison meteorite, which fell in Australia in 1969, contained more than 90 different amino acids, the building blocks of proteins. Only 19 of these amino acids are found in Earth life, suggesting that the chemistry of life could be even more diverse elsewhere. This discovery was revolutionary because it demonstrated that the organic chemistry necessary for life can arise spontaneously in space, without the need for biological processes. More recently, astronomers have detected complex organic molecules in the interstellar medium, including formaldehyde, ethanol, and even sugars. In 2018, scientists announced the detection of complex organic compounds on Enceladus, Saturn's moon, adding to the evidence that organic chemistry is a universal phenomenon. These molecules form in the cold darkness of space, through processes we're only beginning to understand, suggesting that the universe is constantly creating the raw materials for life. Moreover, we've found extremophiles on Earth, organisms that thrive in conditions once thought impossible for life. Bacteria live in boiling hydrothermal vents where temperatures exceed 100 degrees Celsius, in Antarctic ice at temperatures far below freezing, in highly acidic or alkaline environments that would dissolve human tissue, and even in the radioactive water of nuclear reactors. Some microorganisms can survive in the vacuum of space, endure crushing pressures at the bottom of the ocean, or enter suspended animation for thousands of years. These discoveries have dramatically expanded our conception of habitable environments. If life can exist in Earth's most extreme environments, what might exist on worlds with different conditions entirely? The discovery of extremophiles has led to the concept of follow the water being replaced by follow the chemistry. While liquid water remains the most promising indicator for life as we know it, we now understand that life might utilize other solvents or exist in environments we previously dismissed as sterile. This has expanded the list of potentially habitable worlds dramatically, from a handful of candidates to potentially thousands or millions of environments where some form of life might exist. Our solar system. Promising neighbors. The search for life doesn't require us to look beyond our own cosmic backyard. Several worlds in our solar system show tantalizing potential for harboring life, past or present. And the more we explore these worlds, the more promising they appear. Mars has long captured our imagination as a possible abode for life. While its surface is now cold and dry, with an atmosphere just 1% as dense as Earth's, overwhelming evidence suggests that ancient Mars had flowing rivers, lakes, and possibly even oceans. Satellite images reveal dried river valleys, ancient shorelines, and mineral deposits that could only have formed in the presence of liquid water. The Curiosity and Perseverance rovers have found organic molecules and detected methane in the atmosphere, both potential biosignatures. Seasonal variations in methane concentrations are particularly intriguing, as they could indicate ongoing biological processes beneath the surface. What makes Mars especially exciting is the evidence of recent water activity. Dark streaks called recurring slope lineae appear seasonally on Martian slopes, possibly caused by flowing briny water. Underground reservoirs of liquid water almost certainly exist, protected from the harsh surface conditions by kilometers of rock and ice. Recent radar data suggests a large lake of liquid water beneath Mars's south polar ice cap. If life ever arose on Mars during its wet period, billions of years ago, it might persist in these subsurface havens today, perhaps having adapted to the increasingly harsh conditions as the planet dried out. The implications of finding life on Mars would depend on its relationship to Earth life. If Martian life shares a common ancestor with Earth life, it would suggest that life originated on one planet and transferred to the other via meteorite impacts a process called panspermia. However, if Martian life has a completely independent origin, it would be the most significant discovery in the history of biology, proving that life arises readily when conditions permit and suggesting that the universe is full of life. Europa, one of Jupiter's moons, may be the most promising location for life in our solar system. Beneath its icy crust, which ranges from a few to tens of kilometers thick, lies a global ocean containing more water than all of Earth's oceans combined. Tidal forces from Jupiter's immense gravity create friction that keeps this ocean liquid and might drive hydrothermal activity on the ocean floor, similar to the vents on Earth that support thriving ecosystems independent of sunlight. These hydrothermal systems on Earth host tube worms, clams, crabs, fish, and countless microorganisms that derive their energy not from the sun, but from chemical reactions between the hot vent fluids and cold seawater. The chemistry of Europa's ocean appears promising for life. Observations suggest the presence of salts similar to those in Earth's oceans, and models indicate that Europa's sea floor might be in contact with the rocky interior, allowing the exchange of minerals and energy sources. The planned Europa Clipper mission, scheduled to launch in the 2020s, will search for signs of life in plumes of water vapor that appear to erupt from Europa's surface, much like the geysers on Enceladus. The spacecraft will analyze the composition of these plumes, searching for organic molecules, salts, and other indicators of a habitable ocean environment. Enceladus, a small moon of Saturn only 500 kilometers in diameter, has surprised scientists with dramatic geysers that shoot water vapor and ice particles hundreds of kilometers into space. The Cassini spacecraft flew through these plumes dozens of times and detected organic molecules including complex hydrocarbons, salt indicating an ocean in contact with rock, and silica nanoparticles that could only form in hydrothermal environments with temperatures above 90 degrees Celsius. The chemistry observed is strikingly similar to that around Earth's hydrothermal vents, where life flourishes without sunlight. What makes Enceladus particularly exciting is the accessibility of its ocean material. While Europa's ocean lies beneath kilometers of ice, Enceladus literally spews ocean water into space where we can sample it. A relatively simple mission could fly through these plumes with instruments designed to detect biological molecules or even capture intact microorganisms if they exist. Some scientists argue that Enceladus should be our highest priority target in the search for life because of this unique accessibility. Even Titan, Saturn's largest moon, presents an exotic possibility for life utterly unlike anything on Earth. Titan has a thick atmosphere actually denser than Earth's and stable liquid on its surface, though instead of water, These are lakes and seas of liquid methane and ethane. With surface temperatures around -180 degrees Celsius, water ice is as hard as rock on Titan, while methane plays the role that water does on Earth, cycling between liquid, gas, and solid states. Some scientists have proposed that life could potentially use different chemistry on Titan, with methane playing the role that water does for Earth life. In 2015, researchers showed that cell membranes called exotosomes could theoretically form and function in liquid methane. While speculative, this reminds us that life elsewhere might not resemble Earth life at all. Titan also has complex organic chemistry in its atmosphere, creating an orange haze of hydrocarbons that slowly rain down to the surface, building up deposits of organic material that could potentially serve as raw materials for life. The Dragonfly mission, a rotorcraft lander scheduled to arrive at Titan in the 2030s, will explore this alien world, analyzing the organic chemistry and searching for signs of prebiotic chemistry or even life itself. Titan represents the ultimate test of whether life requires Earth-like conditions or whether the phenomenon is more universal and adaptable than we imagine. Exoplanets, a universe of worlds. The discovery of planets orbiting other stars has revolutionized our understanding of planetary systems and dramatically improved the odds for finding life. Before 1992, we knew of no planets beyond our solar system. Today, we've confirmed more than 5,000 exoplanets, with thousands more candidates awaiting confirmation. This represents a profound shift in our cosmic perspective. We now know that planets are the rule, not the exception, and that planetary systems are as common as stars themselves. These discoveries have revealed a stunning diversity of worlds beyond anything science fiction had imagined. We found hot Jupiter's gas giants orbiting closer to their stars than Mercury orbits our Sun, with surface temperatures exceeding 1,000 degrees Celsius and years lasting just a few Earth days. We found super-Earths, rocky planets larger than Earth, but smaller than Neptune, a planetary type that doesn't exist in our solar system but appears to be extremely common elsewhere. We've found planets orbiting binary star systems, creating alien skies with two suns, planets around neutron stars bathed in deadly radiation, and rogue planets drifting through space without any star at all, frozen worlds lit only by starlight. Most exciting are the potentially habitable worlds. Proxima Centauri b, orbiting our nearest stellar neighbor just 4.2 light-years away, sits in its star's habitable zone. While we don't yet know if it has an atmosphere or water, its proximity makes it a prime target for future study. With current technology, we could send a small probe there in about 20 years, and even more ambitious proposals suggest that laser-propelled nanosatellites could make the journey in just a few decades. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 of which orbit in the habitable zone, a remarkable system that offers multiple opportunities to study potentially habitable worlds around a single star. Kepler 452b, dubbed Earth's cousin, orbits a Sun-like star in the habitable zone and could potentially have liquid water on its surface. It's about 60% larger than Earth and orbits its star in 385 days, remarkably similar to Earth's year. If it has a rocky surface and an atmosphere, it could be remarkably Earth-like in its conditions. Dozens of other candidates show similar promise, each representing a potential world where life might have arisen and evolved. The next generation of telescopes will allow us to analyze the atmospheres of these distant worlds, searching for biosignatures, chemical signatures that could indicate life. The James Webb Space Telescope has already begun analyzing exoplanet atmospheres with unprecedented precision, detecting water vapor, carbon dioxide, and other molecules. Future observations might detect oxygen in large quantities, especially combined with methane, which would be compelling evidence for biological activity. On Earth, oxygen persists in our atmosphere only because photosynthetic organisms constantly replenish it. Without life, chemical reactions would quickly remove it. Other potential biosignatures include phosphine, a gas that on Earth is primarily produced by biological processes and was controversially detected in Venus's atmosphere in 2020. Dimethyl sulfide, produced by marine phytoplankton on Earth, could serve as another biosignature. Some scientists have even proposed searching for industrial pollutants like chlorofluorocarbons, which would indicate not just life, but technological civilization. The search for technosignatures. While microbial life might be common, intelligent, technological civilizations could be extraordinarily rare. Yet, if they exist, they might be detectable across vast distances through the signals they produce, whether intentional or inadvertent. SETI. The search for extraterrestrial intelligence has been systematically searching for artificial radio signals from space since the 1960s. While we haven't detected any confirmed alien signals yet, we've only searched a tiny fraction of the sky at a tiny fraction of possible frequencies. It's like searching for a specific song on a radio by sampling one station for 1 second each year. The absence of detection tells us little about whether signals exist. The famous WOW signal detected in 1977 remains unexplained, a powerful narrowband radio signal that appeared to come from the direction of Sagittarius, matching the expected characteristics of an artificial signal. Yet it has never been detected again, despite repeated searches of that region of sky. Modern SETI efforts have expanded beyond radio waves. Scientists search for optical signals, laser pulses, that an advanced civilization might use for communication or energy transmission. Lasers can deliver focused, high-energy signals across interstellar distances more efficiently than radio waves for certain applications. We look for anomalous infrared signatures that might indicate Dyson spheres or other megastructures built by highly advanced civilizations to capture energy from stars. While a complete Dyson sphere remains in the realm of speculation, even partial structures or swarms of solar collectors could produce detectable signatures. We also analyze the light curves of stars for patterns that might indicate artificial structures like orbital solar panels, space habitats, or other constructions. The transit method, which detects planets by observing the dimming of starlight as they pass in front of their stars, could potentially also detect artificial structures if they're large enough and positioned appropriately. One particularly intriguing case is Tabby's star, officially known as KIC 8462852. This star shows bizarre, irregular dimming patterns unlike anything we've seen before, with brightness drops of up to 22%, far more than a planet could cause. While the most likely explanation involves natural phenomena like dust clouds or swarms of comets, we cannot yet completely rule out artificial structures. Subsequent observations have shown that the dimming is wavelength-dependent, favoring natural explanations, but the star continues to behave strangely. This reminds us that the universe might surprise us with evidence of intelligence in ways we haven't anticipated. The Breakthrough Listen initiative, funded by billionaire Yuri Milner, represents the most comprehensive SETI effort to date. Using the world's most powerful telescopes, it searches for both radio and optical signals from the million nearest stars, scanning billions of radio channels simultaneously. The project generates enormous amounts of data that are also analyzed by citizen scientists through projects like SETI Home, which harnesses the computing power of millions of volunteers worldwide. The Great Filter, a troubling possibility. The apparent absence of detectable alien civilizations, despite the vast age and size of the universe, has led to the Great Filter hypothesis, proposed by economist Robin Hanson. This suggests there is some extremely difficult or improbable step in the evolution of life that prevents civilizations from becoming spacefaring and detectable. The crucial question is, where is this filter? If the filter lies behind us, perhaps in the origin of life itself, the evolution of complex cells, the development of multicellular life, or the emergence of intelligence, then we may be extraordinarily fortunate to exist. But our future could be bright. Each of these steps might be so improbable that it occurs only once in billions of worlds, making Earth truly unique. In this scenario, the silence of the cosmos is explained by our incredible rarity, and our survival and expansion into space could transform the galaxy. However, if the filter lies ahead of us, it suggests that something catastrophic typically happens to civilizations at roughly our level of development. Perhaps technological civilizations inevitably destroy themselves through nuclear war, environmental collapse, engineered pandemics, nanotechnology gone wrong, artificial intelligence that turns hostile, or other existential risks we haven't yet imagined. The fact that we see no evidence of advanced civilizations billions of years ahead of us could indicate that very few civilizations survive their technological adolescence. This possibility makes the search for even simple microbial life elsewhere crucial. If we find that life arose independently on Mars or Europa or Enceladus, it would suggest that the origin of life is relatively easy, meaning the Great Filter likely lies ahead, in the path from simple life to spacefaring civilization. This would be simultaneously a thrilling discovery and a sobering warning about our own future. Conversely, if we search thoroughly and find no evidence of life anywhere else in our solar system, it might suggest that the origin of life is the Great Filter, placing it behind us and improving our odds of long-term survival. Some scientists propose that the filter isn't a single event, but rather a series of increasingly improbable steps, like a cosmic obstacle course where each stage eliminates most participants. Others suggest multiple parallel filters. Perhaps some civilizations destroy themselves with war, others with environmental collapse, and still others simply lose interest in space exploration and turn inward. The diversity of potential filters makes predictions about our own future even more uncertain. UFOs and UAPs, separating signal from noise. The topic of UFOs, recently rebranded as Unidentified Aerial Phenomena, UAPs, by the U.S. government has long been dismissed by serious scientists as pseudoscience, relegated to tabloid headlines and conspiracy theories. However, recent official acknowledgement of unexplained observations by military personnel has brought renewed attention to the topic and forced a more serious scientific examination. In 2021, the U.S. Office of the Director of National Intelligence released a preliminary report analyzing 144 UAP incidents reported by military personnel between 2004 and 2021. The report could only explain one incident with high confidence. The others remained unexplained, with 18 displaying characteristics that seem to defy known physics. Extreme acceleration, hypersonic speeds without visible propulsion, or sonic booms. Transmedium travel between air and water without apparent loss of speed, and flight patterns that would subject any conventional aircraft or pilot to crushing G-forces. It's crucial to emphasize that unexplained does not mean alien. The most likely explanations involve sensor artifacts, atmospheric phenomena, classified technology, or foreign adversary aircraft. Many UAP sightings can be explained as weather balloons, commercial drones, optical illusions, or misidentified conventional aircraft. The human brain is prone to pareidolia, seeing patterns in random stimuli, and eyewitness testimony is notoriously unreliable, especially for brief, unexpected events. However, the fact that government officials now take these reports seriously enough to study them systematically represents a significant shift. The Pentagon has established the All-Domain Anomaly Resolution Office, AARO, to investigate UAP reports using scientific methods. Some cases involve multiple independent sensors, radar, infrared cameras, and visual observations, simultaneously recording objects performing maneuvers that challenge conventional explanations. While these could still involve mundane explanations we haven't considered, they warrant scientific investigation rather than dismissal. A rigorous scientific investigation of UAP could either rule out exotic explanations or, in the unlikely but fascinating scenario, provide evidence worth deeper investigation. The challenge is separating genuine anomalies from the noise of misidentifications, hoaxes, and sensor artifacts. This requires careful data collection, rigorous analysis, and openness to following the evidence wherever it leads, without either premature dismissal or uncritical acceptance of extraordinary claims. Alternative biochemistries. Life not as we know it. Our search for life naturally focuses on life as we know it. Carbon-based organisms requiring liquid water. But could life exist in radically different forms? This question pushes us to think more deeply about what life actually is, and what fundamental requirements it must meet. Silicon shares some chemical properties with carbon, and sits directly below it on the periodic table, leading to decades of speculation about silicon-based life. Silicon can form chains and rings like carbon, and silicon compounds are abundant throughout the universe. However, silicon's chemistry is less versatile than carbon's. Silicon-silicon bonds are weaker than carbon-carbon bonds, and silicon compounds are generally less stable, especially at high temperatures. Silicon dioxide, essentially sand and glass, is extremely stable and unreactive, unlike the versatile carbon dioxide that life cycles through constantly. While pure silicon-based life seems unlikely, hybrid biochemistries incorporating both silicon and carbon might exist, or silicon might play structural rather than metabolic roles. Life on Earth uses water as its solvent, the medium in which biochemical reactions occur. Water has unique properties that make it ideal. It's an excellent solvent for many compounds. It remains liquid over a wide temperature range. It expands when it freezes, causing ice to float and insulating water below. And its molecules are polar, allowing complex chemistry. But other liquids could potentially serve this role under different conditions. Liquid methane and ethane, like those found on Titan, could theoretically support life using different chemistry. Such life would operate at temperatures around -180 degrees Celsius, with all biochemical processes occurring much more slowly than in water-based life. The entire planet would essentially be operating in slow motion from our perspective. Methane-based life might use hydrocarbons where we use amino acids, and might breathe hydrogen instead of oxygen. While we have no evidence for such life, its possibility expands our search parameters dramatically. Ammonia remains liquid at lower temperatures than water and could support life on cold worlds. Ammonia is also a good solvent, and life based on ammonia biochemistry might thrive on worlds too cold for liquid water. Sulfuric acid, despite its corrosive nature, has been proposed as a potential solvent for life in the upper atmosphere of Venus, where sulfuric acid droplets float in relatively temperate conditions. We might also consider forms of existence that don't fit our traditional definition of life at all. Life, as we define it, requires metabolism, energy processing, reproduction, and evolution. But could there be self-replicating patterns in plasma within stars? Could magnetic or electrical fields organize into complex information processing structures? Could there be life in the quantum realm, or consciousness that arises in exotic forms of matter? While highly speculative, these possibilities remind us that we should be careful not to let our definition of life blind us to forms of existence we haven't imagined.